Hi, sir. I have a
Jet,
question, but it's not for the assignment.
go ahead, Kieran.
For I know we have to do the two makeup classes for the Monday and Tuesday class, right? But
Yes.
the class that we have to do for the Tuesday class is on Carnival Friday. So I was wondering if we could switch them since this class is online. Because the road will
Um,
be kind of a mess for Carnival Friday.
mhm. Okay, I understand. Um, how do the other students feel about that?
Wait, what day, sir?
Okay, so what Kieran is proposing is that the makeup class for signals and systems, instead of doing it on the 7th of March, right? He wants to do the well, he's suggesting to do it on the 28th of February. So we will have two classes that week. However, if we do that, that means that the makeup class for embedded systems will be the following week, right? The 7th of March.
So we can do the makeup class on say this week, but I don't know if anybody's scheduled for Friday, this Friday.
You mean the embedded systems?
Well, our systems. If you could have it like this Friday coming and just done with it.
The embedded systems class?
Yeah.
Okay. How you feel about that, Kieran?
Yeah, that could work if
In
everybody
next
wants.
week. Next week
Yeah,
is Carnival week. Like
yeah.
in
Next
our
week is
loss, right?
Carnival.
Okay,
No,
okay.
next week is the before Carnival, but what
Yeah.
happens is we have today's signals and systems on Mondays, and there's another class, embedded systems, on Tuesdays.
On a
And
Tuesday. All right.
yeah, there are many students who are in both classes.
Oh, okay.
So we initially had planned to have the makeup class for embedded systems on the 28th, which is well, Carnival Friday for
Yeah.
Carnival. And we would have done the makeup class for signals on the 7th of March,
Okay. I see.
right? Let me see. Well, okay.
Excuse me, sir.
Yes,
Would it be
Micah.
possible to just move the signals and systems to this Friday instead of the embed systems? I leave the embed systems as it is.
Well,
Because
go ahead.
yeah, no, because this Friday I won't be able to, if it's a physical for embed systems, I won't be able to make that.
Okay. All right, okay, I understand. Well, I think what Kieran wanted was to move the embedded systems because of okay, so you're thinking just do the classes 1 week earlier. All right. It's Friday. Okay. I see some persons saying
So
no.
that signals class on the 7th. That's a lab or something or a normal class?
No. It's a normal class. It's but it's to make up for the Carnival Monday class. Now, the other thing
Right.
about that class on the 7th is that is scheduled to be the class before the midterm exam. So I want to do some revision on that class.
Okay.
Right?
Yeah.
Let me see. Okay, so 28.
But excuse me, sir, if we would to say have embed systems on the 28th and signal systems on the 7th, signal systems would be online, right?
Yes, it will be on.
Then I don't see the problem with if we had embed systems on the 28th and signal system on the 7th, because I don't think carnival traffic should cause any problems then, right?
Is the
But I,
28th is the problem?
yeah, I think what Kieran's saying, on the 28th, there may be people in the carnival mood might be, getting into that spirit.
Oh,
So
alright.
yeah, the road may be busy.
I don't know. I don't really celebrate carnival, so I'm not really sure about
And
that.
Micah, do you have any issue, and by extension, the class, if we switch the signals and systems and the embedded system? So we have the signals and system makeup class on the 28th, and we do the embedded systems makeup class on the 7th of March.
Okay, so just to clarify, you want to have the signals and systems on the 7th and the embed systems on the 28th. Just
No,
as
no, we want to swap that. So that's how it is now. Let me see if I can bring up the two course maps side by side. Students who are only in signals and systems, please bear with us a little bit. Get the embedded systems. Okay. Yeah, just share my screen. I'm trying to see if I can get both of them side by side. I need to do the entire screen. Okay, you all seeing the screen there with the two course maps?
Yes, sir.
yeah.
I want to try to see if I can get them as
Excuse me, sir. If you go to the top of Word, right on the left side, the X, you should see a drop-down menu that will even out all these the two split screen. To the icon second to your right. So
second.
yeah, no, back to your left. It's right next to the X on the left. Though.
Well, the thing is, I have two monitors, so it just goes on to the other one.
All right, no,
Yeah,
because you were there just now. It's like with the close, with the X off, it's like the icon right after that. It was like a
This one?
square. No,
Oh.
to your
This
right.
one? This one?
No, it's literally left of the X, so the close off icon.
This one?
Yeah. Yeah, if you hold it, see, it'll just split screen it.
All right, I'm not sure. All right, let's see if we could do. Can you all see this, right?
Yeah.
Okay, let's see if we could. Okay, good. All right, so as it is now. Okay, so today is the 17th. We're here, and tomorrow is the 18th, right? Okay, so this is about it. So the plan is to do next week, we're going to have class as usual, 24th and 25th. And then, okay, so then the 28th, we propose to do lab 4. And on the 7th, we propose to do the makeup class for signals. Okay, so what we are considering is we will do, I'll just put it in red or something. So we will do this class on the 7th of March. So this is what we're proposing. We want to do this. We want to do this class on the 7th of March. So this is a new class. And we want to do this one on the 28th February. I have that right? Kieran, right? That's good, right?
Yes, sir. Yeah.
Right. Okay, good. So let me just scratch this off with the visual. All right. So this is what we're proposing, right? So next week we will do 2 signals classes, and then we will do the makeup class for the embedded systems the following week, the 7th of March. All right. How the class feels about this? General consensus. Anyone has any issues with this? Tell me.
And let's repeat what I said. So I said next week we will have 2 classes for system and signals, one on Monday and one on Friday, and after the following Friday, you will have our embedded class, correct?
Correct. Yeah. So you have embedded week after week.
So I was in the 28th class will be like a revision for the midterm.
Right. So the 28th, which will be the second class, will be a revision. Now, the only thing I a little concerned about, but I want to just highlight for you all is the next class we see each other, or the next class we have after the 20th is the 10th of March, which is the midterm. So please, please take some time to revise, right?
Yeah, about a couple of days.
Yeah, it's going to have some time in between. I don't want anyone
No, I think it's better that way, 'cause after you get a revision, you have something to reflect with before the midterm.
Right, so you'll have about 2 weeks
Yeah.
to, well, a week and a couple days. All right. Okay, well, so far everybody says they are okay with that. Okay, let me ask the other side of it. Anybody not okay with this? All right. So nobody says anything. Okay, so we will go with this. But what I have to do, I have to run this by the embedded systems class tomorrow, right? Just to make sure these students are okay with this. Right, so tomorrow I will do that, and then next week, Monday, I will, actually, no, I wouldn't do next week, wait until next week, Monday. Once the students in embedded systems confirms, I will send out a broadcast confirming the dates for the makeup class. All right, everybody okay?
Yes, sir. Thanks, sir.
Okay, welcome. If anybody has any issues with it, please let me know, right? Please let me know, because the signals systems class is online, so it might be a little easier to make adjustments, but the embedded systems is face-to-face, so I need to make sure the embedded systems people come out for that class. Right. All right, so let's do like this. Yeah, Joseph, question?
Yeah, I just remember I was gonna ask about the assignment. So if we just taking a snapshot of the solution and just compile it to a PDF and submit.
Oh, yeah, yeah. So the assignment, you could do it a couple ways. You can write it on paper, and then you could take some photos of it and upload it. Or if you want, you could type some info, like what you could type out in a Word document, and then take a snapshot of the graphs and add it to the page, like insert it as a picture. So up to you how you want to go about.
All right, okay.
Right. Now just a couple of reminders about it. Make sure when you draw your graphs, you put the points of interest. So for example, actually, let me bring up the like a note sheet to just demonstrate. This is lecture 2, so just a couple of. Right. So when you make the shifts like this, make sure you put the points of interest. So this, this 0.4. Make sure the amplitude, so you label your graphs accordingly. Right. You don't need to put all the different graduations, but once you put the main points on the graph, so you don't need to put everything. Right. So this one, for compression, for expansion, you put the -4, the 4, and the 2 on the y-axis. Right. So just do that. Remember, when you have these different manipulations to do, to put what sort of manipulation it is, right? So time shifting, compression, expansion, time reversal, amplitude scaling, etc. Right? If anyone wants to go back and upload or re-upload, they can. Multiple uploads to take. All right, that's okay, Joseph?
Yes, sir. That's a question about it. I know the time reversal is the U and the -T inside the brackets, right? But the -U does it have a case where it have a -U instead of the -T? I think I saw that somewhere, but I just wanted to clarify on it if it means the same thing or if it's something different.
Yeah, it is there, but it has a slightly different meaning.
A slight difference.
Yeah, so where that comes in, and like this, for example, this is -T minus UT -2 minus UT -4. And what this means is that you have a unit step starting at 2. This is the T -2. And then you have another unit step starting at T -4, which is this. And when you subtract it, basically you subtract one from the other one. So you subtract the t minus 4 from the t minus 2, and that will effectively get rid of this part because these are all ones. And that's how you end up with only this pulse here in the middle, which is this stuff here. So that's where the subtraction comes in.
Yeah, I understand now. But like how the question have x of minus t.
Right, so the x of minus t is the time reversal.
Right.
So
So it wouldn't
that-
have a case where it have like a minus x in front. That's like how they would phrase the question. Would it
I guess
be
it
like that?
could have, but I didn't put any of that in this.
But would that be a difference or would it be same as this? Say if it was minus x and the t in the bracket.
The minus x and t, yeah, it will be different.
Okay.
Yeah, because that would be like it'll be a negative of the x.
Is there
It'll
a
be
question like
different
that I
how
didn't
the
really
graph-
see when I was going through the solutions now?
Yeah, because I didn't do all the possible combinations of it.
Right, okay,
Also,
okay. Right,
yeah,
that makes sense, yeah.
there are a lot of different ways that you could phrase the question, but I try to focus on some main scenarios to
Yeah.
generally give will give everyone a good understanding of how to do it.
Yeah. I just didn't want to see it in the exam and be like, what I'm supposed to do with this, yeah.
Don't worry
But
about it.
I
We will
understand,
go through
the time reversal. I understand it good.
Okay.
Yeah.
Okay. Well, we will go through some questions. We'll do some in revision for the exam. We'll go through some stuff.
Yeah, cool.
So, but you should be okay. Okay. I think some more persons coming, right? So let me just do this. All right, class. For the persons who came in after we had a discussion here, the discussion is about the makeup classes for the carnival week, right? And it's mainly for students who are doing embedded systems and signals and systems. Okay, so we have a lot of students in this class who is doing embedded systems. So I'll have to, get the general consensus confirmation tomorrow. But this is what we are proposing. So for signals and systems, we want to do the makeup class for the carnival week on the 24th, right? So that's the Friday. So that means next week we will have classes on 2 days, on the 24th and on the 28th, Monday and Friday. And for embedded systems, we will do the makeup class on the 7th, right? So that means we're going to have class next week, Tuesday, and then Carnival Tuesday, no class, but that Friday after Carnival, we will have a class on the 7th, right? General consensus from everyone here is that they agree, have no issues with it. What I will do is tomorrow, I will just run this by the class for embedded systems just to confirm, right? So if anyone has any issues with this arrangement, please let me know, right? Please let me know. All right. There's no questions. Oh, the other thing I spoke about is, well, today the assignment 1 is due. If there are any students who are not able to submit today, just please let me know. And you can submit later. I think I set the link to close next week, Monday, right? But just send me an email or message me and let me know if you have any issues making this evening. All right, so if there are no more questions, let us begin the lecture. Oh, the other thing is the next class after the 28th, right? So next week, Friday, the next class I plan to have is the exam, the in-class exam. So we'll go through some revision next class, which is next week, Friday. And just review it before you all come in, right? So I just have to confirm tomorrow. I plan to confirm the availability of rooms, etc. So by next week, Monday, I will confirm that when we have the in-class exam. Okay, so today is just
Recording in
today's
progress.
lecture, we are going to look at transformations. That is Laplace transform and Z transform. Okay, and just a little reminder of why we are doing this. This is because when we have a problem to solve in the time domain, right, it is very computationally expensive and difficult to solve. So what we can do is we can transform the mathematical equations and solve it in another domain. So for continuous time systems, we use the Laplace transform. And for discrete time systems, we will use the Z transform. There's also a transform called Fourier, but we would not deal with that today. We'll do that another day in class. So the idea really is to first transform the problem into the other domain and then solve the problem in that domain and then do the inverse transform on it and bring it back to the time domain, right? So we're going to see all this come into play. Okay, so the lecture today is going to be a little heavy on math, right? This is one of the math heavy lectures. So if anything is you'll need you need to re-explain anything or go further into any details, let me know. Okay. I'll make sure to we'll do some examples today, and then I think we're going to do some more examples maybe next week to just confirm understanding of it. But before we get into it, just some formal definitions in terms of Laplace and Z transform, right? So the Laplace transform is for continuous time signals, and the discrete transform is the Z transform is for these discrete time signals. So Laplace of L of the x of t is the time domain. The Laplace transform of that is x of s, and that really is the integral from minus infinity to infinity, x of t e to the minus st dt, where s is a complex variable, right? So like complex numbers, right? So this is a complex variable in a rectangular form, sigma plus j omega. On the discrete side, x of z, right, which is the transform of x of t, is the sum from minus infinity to infinity. Because remember, for discrete time signals, it's more like points, right? So you're just adding up the points. On the continuous is the integral, and the integral essentially is the area under the line, under the curve or the signal, right? And yeah, so sum from minus infinity to infinity, x of n, z to the minus n, where z is r e j omega. And this where r is the magnitude and omega is the angle. Now this is the same, well, as complex number again, but this time in the polar form. So remember when we're talking about causal and non-causal systems, if it is, we are going to be dealing with causal systems, so we're going to look at from 0 to infinity, not from the past, right? So that's one-sided part of it. So this is just sort of formal definition of it. You don't have to learn or memorize this, just some math behind the transforms, right? Just some more definitions. So x of s is a function in S and is given by these this polynomial here, right? So there's the numerator and the denominator, and x of s could be factorized by k s minus beta 1, s minus beta 2, etc. over s minus alpha 1, alpha 2, etc. Right? So and similarly for the z transform part. So I have x of z with the same polynomials, similar polynomials to the Laplace, and it could also be factorized. This time k into z minus lambda 1, lambda 2 over z minus gamma 1, gamma 2. Now, those like beta values, if that value makes x of s equals 0, right? So if beta 1 is s, for example, then s minus s is 0. Anything multiplied by 0 is 0, and 0 divided by anything is 0. So you call that value a 0, because it causes the whole function to go to 0. Similarly, for the Z transform part is the same thing. If lambda is a value such that it makes the numerator 0, it causes the whole function to go to 0. In terms of system performance, you don't want that. You don't want 0 gain out of your system. On the other hand, if the denominator goes to 0, so if alpha becomes any value that sends the denominator to 0, in this case now, that's what you call a pole. And what happens when you divide anything by 0? It's basically infinity, right? So your system is considered unstable if the denominator goes to 0, if any of these values goes to infinity. And how to get the infinity is you basically divide it by a smaller and smaller number, right, to get to infinity. Okay, so for example, if it is you have a number, and let's just say you have 1 and you divide it by 0.1, you're going to get 10, right? If you have you divide 1 divided by 0.01, you're going to get 100, and so on. So as the number gets smaller, the answer gets bigger and bigger and bigger. So that's how that infinity comes in. Okay, so that's poles and zeros. Now, there is a concept called a region of convergence, and that is where the complex values of each of the transform converges. And what happens is you want actually to, let me just go to the next slide, right? So how you represent in the S plane or the Laplace plane, remember, is a rectangular, a complex number in rectangular form. So you're going to have the sigma and then j omega here. And what you do is you map the values that give you zeros and the values that give you poles. And you would want your system to operate in a region that does not include any zeros or poles, because that's where you want your system to operate in order to be the most productive. Similarly, in the Z plane, you want to stay away from zeros and poles, right? So this is a 0 value here, and this is a pole value here. So you're going to operate on the outside here, basically, right? So that's the region of convergence. Okay, so that was just some introduction into the transforms, what they are like, and then some terminology and what are the zeros and poles and why you want to stay away from them. So this is something you all have to reference also, right? So this is a transformation pairs in Laplace transform and Z transform. And this table is used to transform something or a signal in the time domain to a signal in Laplace domain, right? So this is the first table here on the left. And on the right, you have another table transforming from the time domain to the Z domain. But this is for discrete. Okay, so if you have a unit, an impulse function in the time domain, it is in the Laplace domain, it is 1. And a unit impulse in the time domain for discrete, it is going to be 1 in the Z domain, right? If you have a unit step in the time domain, Laplace transform is 1 over S, and a unit step in the time domain for discrete, it is either 1 over 1 minus Z to the minus 1 or Z over Z minus 1, right? So basically, if you take this first output here, or this transformation multiplied by Z, you're going to get Z over Z minus 1, right? And there are transforms for different signals that it comes in. So as we go on in lecture, we will make reference to this table, and it will be a bit clearer to you on how to use it. All right, but for now, I just want to introduce this table to you, and this table will be in your question papers, that so you can refer to it. So you need to memorize the values for the table. All right, so now in terms of properties of the transforms, there are certain properties that you could, or operations you could perform in it. So there's linearity, time shifting, time scaling, time reversal, etc. One of the ones we're going to look at a little more will be the differentiation, right? So dx dt in the time domain is just converted to sx of s, right? And if you remember, this was one of the things we spoke about, one of the benefits of Laplace. This is one of the examples, because if you have a higher order differential, so if you have d2x dt squared, that's basically s squared x of s. So it makes that mathematical operation much easier, right? We see an example of that also. Of interest also is down here with the convolution. We spoke about convolution last week. So if we have a convolution of two signals, that is basically Laplace of one multiplied by the Laplace of the second one. So there are similar properties for Z transform, right? And yeah, so they don't have just as we spoke about, they wouldn't have integration in Z, because this deals with discrete time signals, and it's basically a sum, right? So no integration there. Okay, so just following in terms of, okay, so in terms of where we started, right? Remember we said we were going to first transform, then we're going to solve it, then do the inverse transform. So that's what we kind of did here. So this here was the transform. So you're going to use your tables to transform it into the Laplace domain or the Z domain. Then you're going to do some sort of operation on it. Yeah, you're going to solve the problem basically. And finally, you're going to do the inverse transform of it. Right, so there are a couple of points you need to take into consideration with the inverse, right? What you have to do is you are basically going to do the Laplace inverse of the Laplace function, or the Z transform inverse of the Z function, right? To give you back the time domain values. Now, you have two ways to do the inverse transformation. There's you could use some complex integration techniques, but that is really math intensive and out of the scope of this course. And the second way is to use the Laplace and Z transformation pairs, right? Which is basically the same table we looked at to transform it, right? So the same table we looked at to transform from the time domain to the S domain or Z domain, we're going to use the same table and do the reverse, right, to bring it back to the time domain. Now, the answer we get in the S domain or the Z domain may not be in the format that we could easily use the table, right, in terms of the polynomial. So what we need to do is we would need to use something called partial fractions to basically break it down, right, into an acceptable polynomial, and then we could use the tables to solve it, right? So I'm going to teach you a little bit about partial fractions, right? A quick, like a quick sort of reminder on it. Okay, so you're going to be using partial fractions if it cannot be easily transformed back into the time domain, right? And right, okay, so this is how you're going to, the general method for solving it. Okay, so you're going to have a system in the time domain, and you're going to have an input, and then you're going to have the transformation on the input. And remember, the output we said the output y is equal to the input by the transformation of the impulse function, right? That's the h of t for the time domain, or h of n for the z domain. And then in the Laplace or z domain, we do the we will do the transformation, and then we will convert back, right? So I know it right now, everything is just, sort of all new, and you see all the tables and stuff like that, and it's probably a little confusing, but we're going to do some questions right now, actually, and that should clarify everything, right? Okay, so let's get into the questions, right? So you'll see how to actually apply what we spoke about just now and what we have to use. Okay, so when you have to answer one of these questions, a couple of things to remember is, remember the output y, right? Y of s is equal to x of s, h of s, when you're doing Laplace, right? And all that simply is this, right? So you're going to have two signals coming in. Right? Well, you're going to have a signal coming in, right? So x of s, and then you're going to have your system doing a transformation, and you will need to find your y of s. And what we said from last week is, if you know the h of s, which is the transformation of an impulse function, any the output for any known input is just the convolution of h of s by x of s, right? So we don't even need to pass this value through the system. All we need to do is we need to just take a h of s, pass it through the system, and then we do the convolution with the input x of s. Okay, so that's what this is saying here. Right. Okay. Now, you have to determine h of s or h of z from a system equation E, right? And y, or the output of the system, divided by the, or over the input x of s, will give you your h of s. So that's how you're going to get your h of s. So that's the first thing. You need to determine what your h of s is. Secondly, you need to transform the input, right? So you have the input in the format x of t. So you want to transform that into x of s. And to do that, we will use the tables. So now that you have your x of s and you have your h of s, you could find your y of s, right? And that is the x of s, which you find here, multiply the h of s, which you get in the first step. So now that you have your output, then you use your inverse transform tables to get back your y of t. Okay. Now, yeah. So sometimes the system equation not given, they don't tell you the system equation, but there's a diagram that shows you how to determine what it is. Right. So we're going to go through that now. But essentially, what we're trying to do here is we have a system, right? We have a system in the time domain. We are putting in values. There's input values, which is the x of t or the x of n. And you need to know, or you need to predict what your output values are, your y of t, y of n. And what we're basically saying is to go this route in the time domain is very difficult, right? In terms of computationally expensive, intensive, and also how you calculate these sort of values. So what we're saying is we will transform from the time domain into the S domain or Z domain. And in this domain, we will determine what the Y values are. And then we do the inverse transform to give us the answer. So that's essentially what we're doing here. All right, so let's see what's next. Right, okay, so first thing is, in terms of the system equation, yes, so the system equation is not always given, but you could sort of derive it from the question. So there is something called block diagrams that you're going to have to be able to interpret. And what you're doing is you look at one block at a time, one part of the diagram at a time, and you will determine the relationship between the inputs and outputs to the block, right? And then you would combine different relationships, right? You make some substitutions, etc. And essentially you're trying to eliminate any unnecessary middle terms. So you want to get your system equation in terms of y and x only, right? So you combine different relationships, make some substitutions, and then you get your system equation finally. Now, in terms of how to read the block diagrams, there are a couple of blocks that you need to be aware of. So this block here with the sort of triangle, right? This is called a multiplier block. So what this is saying is that the output, so if you look at the arrows, right? So x is going in, y is out, right? So the output y of t is equal to a2 x of t, right? So a2 is like a scalar value. There's this other block that is a integrator block, and the output is the integral of the input. So the output here, w of t, is the integral of the input e of t. All right, so w of t is the integral of e of t. Okay, and finally, one of the main ones is the one of the summing junction. Right, so this is the sum of the output is equal to the sum of the input. Very similar to when you do nodal analysis in electrical systems, right? So you just look at the arrow and the signs on the arrow. So you have the output E of t is equal to x of t. So this plus here means it's plus x of t. And then you have w of t coming in, but this minus here means minus w of t. So E of t is equal to x of t minus w of t. And that's how you look at those blocks. All right, so now we come to a question. So this will give you, let us demonstrate here how we use the what we spoke about earlier to solve a question. Okay, so this is the block diagram of your system, right? So we have here x of n coming in and a y of n. So first of all, because you see an n in these input and output values, you know this is a discrete system, right? Okay. So now what we'll do is we have to find the system equation. But in terms of the question, for this system shown up, yeah, Kelda, question?
So it's just repeat that you said the arrows, which it basically says it's a discrete system.
Oh no, the ends, because you see
Oh.
n and you didn't see x of t, y of t. You know it's discrete.
Of course, yes, sorry.
Yeah. So once you see the ends in the square brackets, you know it's a discrete system. And when you see the t's in the curve brackets, it's a continuous, right? Another giveaway is you see in z minus 1 here. So z is only used for discrete systems. All right, so we need to analyze this, but first let's check the question. So for the system shown above, that's this block system, find the output y of n. So you're trying to find this when the input x of n is equal to 0.25 n u of n. All right, so this is 0.25 n, and this is a unit step of n. So we want to know what is the output when the input is this. So we have this big, this complex system, right? And what we're going to do is we're going to use the transform, same thing. We're going to transform from the time domain to the z domain because it's discrete, z domain. And then we're going to do the, find the output in the z domain, and then we're going to do the inverse transform to get it in the time domain. So that's what we're going to do. All right, so let's see how we do this. Okay. Okay, so this is just a question on top here, right? So what we have to do is this. Find the relationship between y of n and x of n. So we have to find the system equation. That's what we need to do. Remember, I said a couple slides ago that the system equation is not always given. So for example, y of n is equal to u of n by 4 kind of thing like that, right? So we have to find that, and we could find that because we have the block diagram. So I'll show you how we're going to go through how to do that. So first thing is to find the relationship between y of n and x of n, the system equation. Then we're going to convert to the z domain, right? Because that y of n and x of n relationship here is in the time domain. So we're going to convert to the z domain. Then we need to find the h of z. That is the, the system functional operator. But remember, the h of z was or is the value of the impulse function undergoing the transformation, right? Remember, we say when we do the convolution, that was like one of the big breakthroughs and the advantage of convolution. So we need to find this h of z, and then we need to get x of z from the input. They gave us the input, right? They gave us the input in the question here, x of n. So we need to get x of z. So we're going to do a z transformation of that. Now that we have x of z and h of z, well, guess what? We could find y of z, right? Because y of z is x of z by h of z, right? Just to show you, go back. Remember, y of z is x of z, h of z, right? Good. So to do that, we're gonna use the x of z from step 4. That's this here. We're gonna use the h of z from step 3. That's this here. And finally, we're gonna do the inverse. So we had to get it back into the time domain, right? So you see how it, this is exactly what we spoke about in the, the first slide, right? So we have a system, but in order to solve it, right, which is we want to know what's the output when the input is this in the time domain. We first need to convert it into the z domain, right? And then we need to do the operation there, and then we do the inverse transform to get it back in the time domain, right? So
how again the x of z again? The x of z?
x of z, well, I'll show you how to do the x
That
of
was
z.
the table?
Yeah, you have to use the table
Okay.
for that.
Right.
Okay.
Okay.
The thing to pay attention to is the y of the last step. Before we find the inverse, we might need to do some partial fractions, right? Depending on if it is the value is not in the table as is. Okay, but I'll show you all how to go about doing that. So don't worry about it. Okay, so let me get started, right? Yes, so let me get started. Okay, so the first thing is you have to find the relationship between y of n and x of n. So to do that, you're using this block diagram, right? So you just list it as you see it to start with. So y of n is on the output. So you start with your y of n, and that is equal to what? You have a summing junction here. And this summing junction means you're going to add, because it have the plus here, you're going to add x of n, right? So you put the x of n down here. And the next thing you're going to add is, remember, this is an amplifier, a quarter, which is 0.25, right? So 0.25 multiplied by z minus 1. But guess what? This z minus 1 actually has an arrow coming back from y of n. So it's really y of n multiplied by z minus 1 multiplied by 0.25. And that's where you get this value here. Anybody lost on the first part here for the system equation?
Just hold on. It matters in any direction you go.
What do you mean? We'll give an example.
Like how you went, okay, for example, y of n on the right hand side, right?
Mm-hmm.
Then
Or if you
after,
want to put the y of n on the left hand side,
well, I mean,
there's no problem if you do that. But so in that case, what you would do is you would say x of n plus, and what would you add? You would add 0.25 multiplied by z minus 1 multiplied by y of n.
okay, so Mike, okay, I think that's what I want to find out. You have y you have is 0.25, right? Z minus 1, but on the diagram, you do have 0.25.
Oh, no, that is quarter here. Quarter, 0.25.
Oh, okay.
Yeah. So
Okay, so it's okay.
and the reason why I put back the YFN is because this actually comes back here. This is like a feedback. So YN comes back into the system to go here.
The z to negative 1 is not included in this relationship.
Yeah, look at the Z here.
Oh, okay.
Yeah, the Z here.
So the question we did before, you did initially deduce that that'll be 0.25. But that's how you actually find it.
No, no, what we was looking at before. So yeah, The example
think-
uses 0.25 twice. So the
Oh, okay,
input
okay.
is also 0.25, but we'll
Okay,
come
that's
into
one
that.
okay,
coming back to
differentiate
that.
between that. All right.
Yeah, so up in this question, the input is 0.25, but right now we're just dealing with to get the system equation.
Right. So these two are independent of each other.
Yeah.
Right.
So for this one, you want to find y of n. Y of n is equal to x of n, right? Which is this, plus what? You're going to add 0.25 multiplied by z minus 1 multiplied by yn. You have to include this yn here because you see this arrow? This arrow means yn comes back into the system.
And if they don't tell you addition, it's always multiplication.
No, they will tell you. The addition comes from this value here. So this could be either a plus or it could be a minus. So you would know from the diagram what to do.
But the other points not labeled now. So then you have to
Oh,
assume it's
no.
multiplied.
Yeah, no, yeah, these one will be multiplied. Once it's
Okay.
in the line, it will be multiplied.
Okay.
So excuse me, sir. So they would actually tell us in the diagram what to add and subtract. And if you don't see it, you just assume it's to multiply.
Yeah,
So-
well, go ahead.
No, but like in case you had to divide anything, would they tell you that, or is there some way to know that?
Well, the divide will be like this. So this is divided by 4, which is a quarter.
Oh, all right, all
Yeah.
right.
The only reason why the adds come in is because this is a sum and junction. So at this point, you're going to perform some addition or subtraction. So the question will have either addition here or subtraction, depending on what it is, right? So that will be here. Once it's all in the same line, it will be a multiplication or division. Well, 1/4 is 0.25, right? Right, so I want to make sure everybody comfortable with this part so far, right? So everybody get a system equation.
Yeah, I understand the equation. So it's just my confusion is a bit like with the arrows. It's when you had the xn, but looks like the arrow pointing the opposite direction when you wrote the equation. Is that because of the feedback from yn?
So
Like when yn feeds into
Uh-huh.
z to the power
Yes.
-1 and then feeds back into the 0.25 and then back into the, I think you call it the summon
Yeah,
generator.
the sum and junction, yeah.
Yeah, that the arrows there is the feedback from yn, isn't it? That's why it's like
Yes, yeah.
that. All right.
This is why I found.
two things, sir. Miguel trying to get into the class. You say having
Yeah.
problems getting to Zoom.
I don't see anybody. I don't have any waiting room or anything. He getting any errors? He told you anything?
All the time you're trying to get in class for the past 30 minutes.
That is strange. I don't know.
Well, you
Anybody
should-
had it?
Tell them try rejoining. Oh yeah, but instead of trying to thing in the password, just use the link if anything. And oh yeah, but the password also on Canvas, but just remember to be case sensitive.
Maybe just Kellen, to ask him to try. I can't even invite him. Yeah, ask him if he is using the somebody.
Somebody could just send the link to them if figure it out.
Hold on, let me see if I can get a.
Let me send a link. Oh, let me use the link that I use for him.
Yeah,
Hold on. Right?
I'm gonna paste the link in the chat. Yeah, if you're able to. I think this should be the link. Right, you can probably send him that and ask him. So sorry you're not able to join. I don't know why.
Okay,
Maybe you
okay.
can ask him what error he gets in. Like, is it like he waiting on because of
Excuse me.
Let me know, Kelda, what he says, right?
Yeah, I'll do that. Yeah.
All right. Okay. Yes. Where was I? Right. So we're trying to find y of n in terms of the inputs. So the inputs, you look at the sum and junction here, right? So yn is the output. All the inputs to that, it have two inputs, x of n, and then the second input is this here. A quarter z minus 1 by y. You have to include the y because this y feeds back here into the into this loop. This is generally called a feedback loop. It's used a lot in what they call control systems. It's a big part of electrical engineering, control systems and control systems engineering. They use it out in the industrial plants to model their systems. But yeah, so you have to include that YFN essentially.
So he sent me this thing, he said authentication to the commercial Zoom platform to join the meeting. He had to join here, have to create a Zoom user account.
I really don't know.
I
I've
think
never
so.
tried.
Let's see something.
But ask what he could do if he's on his laptop, if he goes on Canvas and go to the Zoom.
He say he tried that already, guys. First thing I tell him.
Because that's, I know that should work because he's using his UTT login for that. And go to join meeting or the option there. That should be it. Yes. Okay. I don't know. Maybe you could try creating a Zoom account.
That's what, yeah, I think that's what I had to do. I think I got that error once. You had to create, since it's a commercial Zoom account you had to make.
A commercial. No, well then the UTT account will be a commercial account.
I had a problem so once, and when I created the Zoom stuff with, I had to create with the same commercial Zoom account. I create an account with my UTT email, and a problem went away.
Oh. But
It's kind of weird.
You're not
It's
logging
kinda
into that
weird.
now though. You log into another account.
I don't know.
You could even try logging on from the web and the Zoom on the web instead of if the app not working.
I don't know. I think something to do with Zoom being updated. Because I think even my Zoom, when I look at my Zoom app, it has some kind of commercial, something Zoom, this, that.
Oh, it does. Yeah, Zoom and they're updating the stuff quite regularly and it changes some terms and conditions. But I want to believe that once, at least if he uses the UTT, his UTT, the we.utt.edu.tt email or account, it should work there because that's
Zoom, I think Zoom, but it's like, you have both. You have a UTT email and have the commercial account with the UTT email.
what is he telling you now?
I guess he tried.
Okay. Let me see what he says. Hopefully he gets through. All right, let's continue, right? Okay, so first thing is you find the system equation, relationship between y and x. And this is your relationship, right? Y of n, x of n plus 0.25 z minus 1 y of n. The next step is you convert that to the z domain. So this part is, in terms of this general equation is straightforward, right? All you do is you basically put in a capital Y and instead of N, you put in Z, right? And a capital X and Z instead. So this is the conversion to the Z domain. That's all you do. This is straightforward, right? You're going
The capitalizations matter, right?
Yes, it does. It does. You have to put it in capital letters because it is the format for the Laplace and the Z transform. So don't put comma. All right. Yeah, and it have to be Z in brackets or S if it's Laplace. You know a Laplace example. So that's important. You need to put it like that. Now, after we get it in the Z domain, then we're going to find the H of Z. Now remember the H of Z. Let me just go back a couple slides, right? Remember, the H of Z is the relationship between Y and X. So Y of Z is equal to X of Z, H of Z. So H of Z is Y divided by X. So that's essentially what we're going to do here. So H of Z is equal to Y on X, right? So first we just need to simplify this, rearrange some stuff and simplify it a little bit. So we have Y of Z is X of Z plus 0.25 Z minus 1 Y of Z. So we're just going to take this Y of Z, this 0.25 Y of Z here, and we're just going to bring it across on this side, right? And then we're going to factorize out the y as z. So y as z multiplied by 1 minus 0.25 z minus 1. Because when this 0.25 go across, it becomes minus 0.25, right? And that is equal to x as z. X as z remains on this side. So y divided by x, it's going to be 1 divided by 1 over 0.25 z minus 1. All right, everybody follow this?
Why have
Well-
one in front of the negative 0.25?
1, right? Okay, because this was this. Okay, so when we shift it around, this ended up being y as z, right? Minus 0.25 z minus 1 y as z. So if you take the y as z on the outside, it's going to be 1 minus 0.25.
Oh, I factorize. Okay.
Yeah, you factorize that, right?
Okay, no
That's how you
problem.
get y minus.
I know, so I had no itinerary confused with you. I had to laugh. I get
Sorry.
confused.
All right, let me see. Let me see. Let me do this. Let me just add. Let me see. I think I could update this slide. Right? Okay. So when we take that there, right? So when we do this, this becomes this, right? Right. So that becomes right. So we take the 0.25 on the other side, right? So it becomes this now. And then from here, we're going to factorize. Right? So we take the y as z on the outside, and we get 1 minus 0.25 z minus 1.
All right, no, I see. For some
Right.
reason, I wasn't see. I don't see. Don't see.
So excuse me, sir, you basically put the 0.25 z minus 1 on the opposite side equal sign, and then just factorize yz from the entire equation.
Correct.
that it?
Correct. Yeah. So you take y as z out, you factorize it, and then you're going to take y divided by x. So you take the y value here. Well, not the y value.
Wait,
This term here, and put
so
it underneath.
I have a question. After the equal sign, you had x of z. How come you end up with 1 times x of z? X of z.
This one was put in to just kind of make this part. The one was put in, the one was put in here to kind of lead into this y have a 1 here. So basically, x of z is really 1x, right? Like if you have x equals y, it's really 1 by x equals 1 by
Yeah.
y. So essentially, this could have been this, right?
It's like it basically like a coefficient, but you could it's invisible. Put it.
Yeah, exactly. So it's basically this, right? And then you're gonna take your x of z, and you're going to divide. You're gonna take your y divided by x, and then you're gonna divide both sides by the 1 minus 0.25 z minus 1.
Okay, well,
So
I
that's
can't.
it.
So excuse me, sir. So after you factorize the yz out, and after you move everything, you basically first divide the whole thing by you basically cross divide or multiply, whatever you call it, by putting yz divided by x, so on one side, and then you take the the 1 minus 0.25 z1 and divide out by on the other side with the one that's remaining.
Yeah, that's pretty much it. So what we're doing is we're taking this form, this part here, right? And first we divide in both sides by x of z. And if you divide both sides by x of z, you're going to remain with, this is going to be 1, right? And this is going to be divided by x of z, right? And then if you divide both sides now by 1 minus 0.25 z minus 1, you're going to get y over x, and then 1 divided by 0.25 z minus 1.
So basically divide by xz first, then the 1 minus 0.25z to the power 1,
Yes.
negative 1.
Yes.
All right.
Now
Yes, they cross multiplying basically.
I kind of getting lost and I keep finding myself kind of getting confused. So when you have, okay, after you do the factorization, you have y of z, right? 1 subtract 0.25 z to the power 1 equals x of z, right?
Right.
Right. The next step is you factorize, right? So you plot the y, you factorize it?
Yeah, well, yeah, it's already factorizing, I think. Yeah,
No,
there's this
no, no.
part there.
Yeah, okay, yeah, that part, right. But the part on that, I'm trying to figure out why you do that.
Which part here? This one here?
Why
I think
no,
that's when
hold on,
divides the
Micah,
whole.
you're confused.
No,
Yeah,
basically, sir divides the whole equation by x by z. Well, x to the power z. You divide both sides of the equal sign by it, and well, on the right side you already have that, so that cancels out, giving you 1. And on the next side, since there's nothing there, you just leave it as that. So yz multiplied by 1 minus 0.25 by z to negative 1 divided by xz. The next
okay.
one after that is just you're dividing both sides of the equal sign by what's in the brackets, the 1 minus 0.25 by z. Since you already have it on the left side, that just cancels out, which just becomes like yz times 1 divided by xz. And since it doesn't exist on the next side, you basically just divide it over 1. So 1 divided by 1 minus 0.25 by z to the negative 1.
So put this stuff in the square brackets in a different color. In the last 2 lines.
So, Keldon, like, okay, look at that example there, right? So if you have 4y equals to x, right? You could say y divided by x is equal to 1 over 4. Right? Basically what you're doing, first you're dividing both sides by x. Right? If you divide both sides by x, you're going to get 4y over x equals 1. And then if you divide both sides by 4 now, you're going to get this here. And that's essentially what you're doing here. First, with this here, you're dividing both sides by x of z, right? So you're going to get y of z 1 minus 0.25z minus 1 divided by x of z, and that's equal to 1. And then you're going to divide both sides by 1 minus 0.25z minus 1. So that'll give you y over x, and then 1 over 1 minus 0.25z minus 1.
I understand, but I'm just trying to get concrete in my mind what you did. Because, okay, so first you divided by x of z, right?
Right.
And that's how you get the y of z 1
This one here.
subtract 0.25, yeah.
Yes.
All over x of z equals 1.
Correct, yeah.
Right, and this h as z thing, did I just what I for?
Oh, h is equal to y over x.
Oh,
It's just y
okay.
over x, yeah. That's what we call h. That is system operator.
Okay, so h of z, the y over x of z. I'm just trying to equals the 1, and now how you get a 1 over the 0.25.
As I say, if you're going to look at it for a simpler example. So
I
like
think-
this here, 4y equals x. If you want to get y over x, you just divide both sides by x and both sides by 4. So you get y and x is equal to a quarter. It's pretty much the same thing. Instead of x, well, instead of 4 in the example here, is 1 minus 0.25z minus 1.
Wait, but I think it's how you type it out confusing me for some reason.
What might be it is how it's on the same line, right?
Yeah,
So
that is the thing what
again,
confuses me.
you're not getting y over x. You're kind of seeing y divided by x.
Yeah, not trying to work. So my thing is I trying to figure out how the 1 subtract by 0.25 end up on other side.
You just divide this side by it. You divide both sides by it, I mean. So to get rid of it on this side, you have to divide by 1 minus 0.25 z to the minus 1.
Or you just divide by,
yeah,
because you multiply on one side.
Correct.
One.
It's multiplying one on the left side, and on the right side, you're going to have to divide by it to get it.
All right, well, I don't worked out by hand to just
Yeah,
because
yeah.
basically simple algebra. I just getting confused.
Yeah, you just gotta look at it, because remember in terms of, as you say, algebra, remember I saw you solve, like, so you say x equals you say 2x equals 4y, for example, right? To simplify that, you divide both sides by 2. So 2x divided by 2 is x, and 4y divided by 2 is 2y. So whatever you do on one side, you have to do the other side. So here, when you divide by x of z, you have to do it on both sides. So x of z divided by x of z is 1, that's this. And y of z multiplied by 1 minus 0.25 x z minus 1 divided by x of z is this value here. Right? And then to move down, you divide both sides by 1 minus 0.25 z minus 1. Right? What I'll do when I do the next slides, I'll try to put them like this, in this format. Maybe that will help and recognize it, so it'll be a little clearer. All right. Okay, I see Miguel joined in. Miguel, you got through okay? You did anything different?
I got through with my phone, so not the laptop. I don't know
The
what's going on
laptop?
with the laptop. No. So I use my phone right now.
All right, well, I'm glad you could join. I don't know why that.
Yeah, I really don't know what happened.
Did you
I'll
try
check it out
upgrade?
later.
Yeah, try maybe upgrading the app, maybe also.
Yeah, I think I will uninstall. Yeah, I'll do that. I think there's the app itself.
Okay, well, glad you could join.
All
All
right.
right. Okay, so that's h of z, right? So now we have y of z and h of z. The next thing we need to do, let's just go back to the right. So we found the relationship, we converted to the z domain, we found h of z. So the part 4 now, we need to find x of z from the given input. So they told us that the input x of n is 0.25 n u of n. So we know that. We need now to convert that x of n to the x of z. Okay, so this is where we're going to start using tables, right? So this is the tables we looked at earlier. This is just a subset of it because I only included the one transformation we're looking at, right? So how it is you use these tables is you look at a format, right? So we have x of n. X of n is this here, 0.25 n u of n. So what we do now is we're looking at this column, because this is the x of n column. And we're looking for a value here in the format of this, right? So this is our general format. So I already kind of blocked off and highlighted what it is, but this, if you look at this value here, right, this is a of n u of n. A in this case would be 0.25, right? And the nu of n is the same. So that means that the z transform of the x of n is 1 over 1 minus a z minus 1. Now, one thing to pay attention to here, how about this is a little comma here. I don't know if you all seen it, right? But this means that you could transform x of n value in this format to either this one or this one. Any one, it doesn't matter, right? So either one you could use. So we are going to choose this format here. So the z transform of this input value is 1 divided by 1 minus 0.25 z minus 1, where a is 0.25, because that's this here. All right, tell me. You okay with that?
Yes, sir.
You see it? Tell us, all right?
Well, I think I see it. I don't know if you're supposed to put for the final thing like 1/1 subtract by 0.25 z to the power -1 or something. Oh, that's why you do it, man. You do it already.
Yeah, that's it for this part. So this part, all I do is ask you to find the x or z. Now, what you need to do, the technique really here is given the value, right? So given the value, this is the input here. Given this value, you need to look at this column and look for a format that it would fit in, right? So it's definitely not a unit step. Is that impulse is definitely not a unit step only, right? It's not a unit step only. It's not a negative unit step in this format. There's no n-1, right? It's not this one. Going down the line, this one looks like it, right? ANU to the n, where A is equal to 0.25. Right? So you see, okay, this kind of matching the format. But now we have to pay attention to, this is actually two ways to represent it. So you just choose one. So we're just going to choose the first one. It's going to be 1/1 minus AZ to the -1, where A is 0.25. Okay, so that's how you convert your x of n to your x of z. They go from the time domain to your z domain. So just to show you all what we did so far, we did this. We found the system equation. We converted it to the z domain. We found the h of z, and we just found the x of z. So next thing is we're going to find y of z, because we have h and we have x. So we can compute y. And after that, we're going to do the inverse. Right? So
Recording
before we
stopped.
continue, we just take a short break, right? So you come back at 6:19. We come back about 6:30. We just do the attendance. And I'll probably just do some short announcements to repeat for everyone who probably came in late, who we spoke about. We'll continue. So see you guys in 10 minutes. See the assignment, you can let me know in class, and we could go through it afterwards. Secondly, what we were talking about at the beginning of class is to make a slight change in the schedule to make up for Carnival. So initially, on the left here, we have the course map for signals and systems. Okay, so today's the 17th. We're going to have class next week, Monday. And initially, we were going to do the makeup class for that we're missing on Carnival on the 7th. So we're thinking about doing that class on the 28th, right? So if that's the case, next week, we're going to have two classes, Monday and Friday. Keep in mind that the next time we meet after that makeup class, it will quite likely be on campus for the exam, right? So we're going to be doing some revision on that class on the 28th. So please try to attend, okay? And you can do some review for the exam. The course map on the right is one for embedded systems, because this will have an impact on embedded systems. So we have some students from embedded systems in this class, and some who are not. So I need to review them tomorrow. So the schedule will change here also. So initially the makeup class was only 28th. So we will push that makeup class to the following week on the 7th of March. Right? So if anyone in signals and systems has an issue with this, please let me know today, right? Before class ends.
Excuse me, sir. Will
Yes,
these
ma'am.
changes be uploaded to campus?
Yes. So
Yeah, because I had to send a copy of this for transport for the embed systems.
okay. Yeah. So once nobody has any issues with the class today, because everybody's in class right now, okay? So once nobody has issue with this change today, and tomorrow I will discuss it with the embedded systems class. And once they don't have any issues with it either, I will make the changes to the course maps and upload the updated documents to campus. And I'll also send a broadcast on Canvas so you'll know of the changes to the makeup class. All right, so look out for that. Well, tomorrow Embedded Systems finishes a bit late, so maybe Wednesday I'll send that. Okay, so I will discuss, if I forget to talk about it tomorrow, please, someone from Embedded Systems remind me, okay? I shouldn't forget, but in case I do. Right, so any issues with this, let me know, right, from Signals and Systems class. Once everybody's okay, tomorrow we will talk about it in Embedded Systems, and then we will formalize that. Okay, so let us get back to this.
Recording in progress.
So we found the relationship, right, between y and x, that's the system equation. Then we converted it to the z domain. The third step, we got the h of z, which is the system function or the operator, right? And then the last thing we did was find x of z given the input, right? So the input in the time domain was 0.25 n u of n, and we got the z transform of it. And to do that, we had to look at the table. Okay, so you just look at the table, look for something similar in format, and then use the corresponding transform. Okay, so the next thing we need to do is we need to find y. We need to calculate y. So remember, y is equal to x of z by h of z. And x of z, we got it here. 1 over 1 minus 0.25 z minus 1. Right? So that's this value here. And x of z is actually the same thing, right? Remember, it was 1 over 1 minus 0.25 z minus 1. So y is 1 divided by 1.25 z minus 1 squared. Is the same number twice, right? The same same input twice. So that's what you're going to get 1 over 1.25, 1 over 1 minus 0.25 z minus 1 squared. So that is a y of z. So you have that. Now, the last step, what you need to do is you need to find the inverse of that value. So we have 1 divided by 1.25 z minus 1 squared, right? And again, we're going to look at the table, right? So we have the x n in the time domain, and we have the x z. But now we're looking at the table in the other column first, right? So remember, we have the z value, so we're going to look at this now. So we're going to look at this column for a value that is in the same format as this here. And we already highlighted it, but basically it is down here, 1 divided by 1 minus az minus 1 all squared, which is very similar to this format here, right? So if you convert this into the time domain, you're going to get n plus 1 a to the n u of n, right? Where a is 0.25. So your answer is this value up here, n plus 1, 0.25 n u of n. Everybody follow?
So I get this do over number 5. I
Number
get up to
5.
4 and I understand 6, but I understand 4, but 5 kind of lose me.
Yeah.
How you end up there?
Right. So y is x by h, right? X of z by h of z. And if you go back, right? So remember, x of z was 1 divided by 1 minus 0.25 z to the minus 1.
Yeah.
So that is this first value here.
Yeah, that's
And
x as z.
Right. And then h of z, well, h of z ended up being the same value, right? When we work it out. So
Yeah.
it's the same value squared. So that's why you get 1 divided by, 1 divided by 0.25 z to the minus 1 squared.
Okay, I will actually strip it now. Thanks.
Yeah, no, don't, that's fine. It's important to clarify if you have any doubts now, right? Rather than in the exam. So that's fine. Right. So then when you get this now, you look for the value table that represents it, or closest to it in terms of the format. And it's this here, 1 divided by 1 minus a to the z minus 1 squared, where a is 0.25. So then you use the relevant time domain transform. So that's how you're going to get here YFN now. Now, what we did here essentially, right, is essentially what we did here is we calculated the output y of n for the input x of n, where that was equal to 0.25 n u to the n. And we did that by finding the system equation, right? So that's the first thing here. So we use the block diagram to find the system equation. Secondly, we converted that system equation into the z domain, or transformed it into the z domain. Thirdly, we found h of z, the system function, right? So that was y of z over x of z. And fourthly, we took the input, transformed it into the z domain, right? Fifth thing we did is we did the calculation in the z domain. So y is equal to x by h. And now that we have the answer in the z domain, we need to convert it or transform it back into the time domain. And we use the table to do that. So that is, basically the process we spoke about in the Big Day lecture. That's exactly what we did. Right now, we were, in this case, the result we got from part 5 here, meaning this value matched pretty well into one of the values in the table. But it is possible for that not to be the case, right? And if that is not the case, we need to use partial fractions to make it simpler. So partial fractions is a decomposition in process of breaking up rational expressions in simpler components of fractions. Now, it has a couple steps to do to get it to work, right? But basically, you want to make sure the highest power of the numerator is smaller than the highest power in the denominator. So that's when you could break it up into partial fractions. So let me just show you an example here. So this is a table you use to how you would split a number into partial fractions. So if your denominator, right? So when it is we got through with something and the denominator was in this format, ax plus b, right? The partial fraction would be a over ax plus b. And if it is in ax plus b to the k, right, you actually split that up. So a1 over ax plus b plus a2 over ax plus b squared plus whatever until you go up to the value k. And then this could even be further broken down, right? So you have ax squared plus bx plus c, which is a very popular one, quadratic equation, right? So essentially what we're going to do is when we get an answer for the y of z or the y operation, we need to break it into smaller fractions to get it to resemble or to fit one of the models in the table. And that's what we're going to use partial fractions for. So just as an example of partial fractions, right? So let's just say we have this this here, 8x minus 42 divided by x squared plus 3x minus 18, right? This could be split up into 8x minus 42, and then the denominator, you could actually factorize it into x plus 6 multiplied by x minus 3, right? So if it is you multiply these, you're going to get x squared plus 6x minus 3x minus 18, and then 6x minus 3x is 3x, right? So in this format now, right, you use the tables to determine the partial fractions. So you have one term in x plus 6 and the next term in x minus 3. So that's this here. This is the factor in the denominator. So it could be split up into a over ax plus b. This is the general term for the partial fraction. So the first denominator is going to be if you take the first denominator into consideration, it's going to be a over x plus 6. And then you take the second denominator, it's going to be over x minus 3. So from this point, because the two denominators are the same, right, you could combine the numerators. Basically, you could work on the numerators only, right? And so we have 8x minus 42 over this is equal to a into x minus 3 over x plus 6, x minus 3, plus b into x plus 6 over x plus 6, x minus 3. Okay, so how do we get this, right? Remember, okay, so we have this, and we split it up into these two parts here, right? So this whole value, this fraction here, can be split up into a over x plus 6 plus b over x minus 3. So the first thing you do is you're going to say, all right, so let's get a common denominator between all of these fractions. So x squared plus 3x minus 18, we know this is equal to the combination of this, right? So in order for us to get a common denominator for the a term and the b term, we multiply by the other term here, right? So that's where you get, it was a over x plus 6. So you're going to say a over x plus 6 multiplied by x minus 3 divided by x minus 3. Right? And this is b over x minus 3. You're going to multiply by x plus 6 and divide by x plus 6 to get the common term. Right? Basically, there's the LCM there. Right? And now because because they all have a common denominator, you could just deal with the numerators, right? So 8x minus 42, which is this here, is equal to ax minus 3 plus b into x minus 6. So now that we have the numerators only in this sort of equation, we have to eliminate one of the values to solve for the other one. So first, let's look at eliminating a and solving for b. So if we substitute x equals 3 in this equation, this is going to go to 0, right? Because 3 minus 3 is 0, 0 by a is 0. So you're going to get 8 by 3 minus 42 is equal to, well, 3 minus 3 by 8, that's 0, plus b into 3 plus 6, so that's 9, right? So that's 18 equals 9b, b is equal to minus 2. And then, now that we find a value for b, right, now we need to get a value for a. So if it is we eliminate b by substituting x equals minus 6, we can get a. So 8 multiplied by minus 6 minus 42, right, equals to a multiplied by minus 6 minus 3 plus b into minus 6 plus 6. So this is going to go to 0, right? 8 6 is 48, minus 48, minus 48, minus 42, right? Minus 90, right? And then we're going to have minus 9a. So a is equal to 10. So now, if we look for the, we substitute what a and b are, right? Remember, if we go back here, it was a over x plus 6 plus b over x minus 3. And a was 10. So 10 over x plus 6 minus 2, right? Because b was minus 2. Minus 2 over x minus 3. Okay, so that's a quick sort of tutorial on partial fractions. Right? And this is what we have to use if it is the equations don't simply fit into the tables. We just have to split it up even further. Right? So if it is a value like this, for example, you need to split it up even further. And then if it splits up into like this here, 10 over x plus 6 minus 2 over x minus 3, you could get that easier from the table. Right? So partial fractions is something we might use. Okay, we will do the partial fractions in the next example. So you'll see how it works there. But basically what we're going to use is we're going to use these two mainly, right? In the format ax plus b and ax plus b to the power of some value. Right? So you split it up into those two values there. Okay, so let's look at a continuous time system now, right, with the transform. So here we have a system, relationship between y of t and x of t, right? And it passing through some summing functions. This is an integrator, another summing function, an integrator, and this is two multiplier functions, right? Now, this question actually breaks it up into different pieces to find the end system function. So first, you need to write a relationship between e of t in terms of x of t and y of t. So you want to find this here, e of t in terms of x and y, right? So we see here already e of t, and it has a summing junction. It's going to be x of t minus a2 y of t, right? So we just deal with it one by one. So if we look at a here, right? X of t minus a2y of t is equal to e of t. So that's this value here. So that's the first part of it. The second part is the final relationship for w of t. So a final relationship here now in terms of e of t, right? And then use this expression to derive an equation for first order differential. Yeah, Kelvin.
So you go over part A, I lost.
Part A.
Yeah,
Right.
lost.
So part A, we just did, okay, so this is, eventually we need to find y in terms of x. But because it have different points, the question just kind of going through it one step at a time. So we're just looking at this here for now. So the question, part A, is to find e of t. So you want to basically determine what is e of t. And e of t is equal to x of t, this here, and then have something coming back here. What is this? Minus what? Minus
E2.
multiplied by y. A2 multiplied by y. Right? And that is why, for the first part, right, so the first part, x of t minus a2yt is equal to et. You see that? That's just this part here, right? Just et alone we're looking at for now.
Okay. But
Right.
my question is, but like, there's ever a way are you following the arrows? That is my thing, or you're not following the arrows?
You are following the arrows, but you're not looking at it end to end. You're looking at it from a certain perspective. So you only follow the arrows from E of t. So you're not looking at what E of t going, because you're not interested in that right now. You're just looking at what the arrows are in terms of the relationship with E of t. So you have an arrow going in here, and you have an arrow going in here. So this arrow is x of t, and this arrow is minus a2y of t. So that's all you stop in at E of t.
So basically, EFT is like an output of x of t and a2, negative a2.
Y of t, yes. Yes, that's exactly what it is here.
Okay.
Right?
No,
So that's,
I think I understand it now. Okay.
Yeah, so you can think about it as yes, y of t is the main output, but it has multiple you want to call it sub outputs in between. Right, so that is y of t. So the next question we'll actually try to here. So write the relationship between w of t. So that's w of t here in terms of e of t, right? So first, if we were to just do this one part, w of t is equal to the integral of e of t. So that's this here, right? The integral of e of t dt. Okay, and now the second part is then use this expression to derive an equation for the first differential, right? So if you find the differential of this, you're going to get e of t, right? So the differential of an integral is the term itself. So e of t, and then you differentiate w of t dt. You differentiate in terms of t. Right? So this gets shifted to this value here. Okay. So that's w of t. So the third one is to write a relationship for g of t in terms of w t and y of t. So we're now looking at here now, g of t. G of t, we're just interested in what coming into this summing junction. So you have w of t, which is this part, and then you have what? Minus a1 y of t, which is this here. right? So G at T is equal to W at T minus A1 Y at T. That's how you get this third part. And then the fourth part is to write a relationship for Y at T in terms of G at T. Okay, so again, now we're looking at this point here. So Y at T is equal to the integral of G at T. And then to say again, use this expression to derive an equation for the first differential of Y at T. So to do that, you differentiate both sides. So you differentiate the integral of G at T, you're going to get G at T. And then you differentiate Y at T, you're going to get dy dt, dy of T dt. Right? So that's why you get the first four parts there. Now, the question has, now when you get these first four equations, then you need to find the the differential equation of the system. But you need to show it, you need to basically prove that this is what it is here. d2yt over dt is equal to minus a1 dy dt minus a2yt plus x of t. So essentially, you're going to make some substitutions and get rid of all the E and the G and the W. And you're going to have everything in terms of Y at T and X at T, which is going to be your system equation, essentially, right? So look at it here now. So these are the four equations we got in the last part, right? This is the first one, second one, third one, and fourth one. So first, we are going to look at the second equation and use the value of E at T, right? And substitute that into the first equation. So you have X at T minus A2Y at T is equal to dWt dt, right? So that's how we get this fifth equation. Basically take E at T is equal to this and replace it here. Then we find the differential of 3, right? So, and then we're going to substitute for dWt, right? So the differential of 3 first. So the differential of gt is dgt dt, right? Equals to dWt dt minus a1 dy dt. Right, so that's the differential of it. Then,
So for equation 3, you're just taking it and you're just finding the differential equations of
you find
it, right?
differential. Yeah, you find
That
differential.
is it, right?
Only first, yeah. Right. And then what we're doing is we are going to make dWdt. Remember, dWdt here is essentially what we're trying to replace, right? Because we want to get everything in X and Y. So we need to make dWdt the subject here. So it's going to be dgt dt minus plus a1 dy dt, because it was minus here, bringing this on that side. Right? And now that we have this equation 6, remember this equation 6 is dWdt. So see, so we're going to replace that now. So you're going to get xt minus a1yt equals dgt dt plus a1 dyt dt. Right? So you get this 7th equation now. Right. So now we have the 7th equation, right? Let's put it back here. What we have now, right? Now we are going to differentiate 4. Right? Because we have a term here in dg dt now, and 4 is in g of t. So let's differentiate 4. So if we differentiate 4, we're going to get dg dt equals d2y dt squared. It is a second order differential because this is already a first order differential. So if we differentiate again, it's a second order differential. Right? And then you're going to substitute that, right? So you're into 7. So you have x at t minus a2y at t minus a2y at t. Now we have dg dt, and we need to substitute that. So we are going to say this is now equal to d2y dt squared plus, and the other value, a1 dy dt over dt. Now, if you notice, this entire equation is only in terms of x and y, which is what you want, right? You want it in terms of the output and the input. You're not really interested from a system equation perspective, these other values of E at T, W at T, G at T, and things. You just want in terms of the output and the input. Now, we have the value here, but we have to just rearrange it to prove this here. right? So if it is, put the second, leave the second order differential here in front, and then we bring across the a1 dy t dt, you're going to get minus, because we're bringing it across, minus a1 dy dt, that's this here, minus a2 yt, which is here, plus x at t. So that's how you prove this equation here. Now I know that was quite a lot of operations there, so you might need to review that, right? But anything right now you want me to review? Basically, we look at each of the different blocks and we make changes.
So you
Yes,
keep substituting back into the main equation.
Yeah, well, it keeps substituting it to essentially get rid of all the E, the W, and the G, the middle terms, and you
Right.
wanted to get it in terms of X and Y only.
Correct.
Right? Okay. Right. So that's the first part. Well, not first part, but that's the first thing you have to prove, basically. The second well, part F is given two values, scalar multipliers. So they're telling you now A1 is equal to 7 and A2 is 12. They're actually giving you values for that. And all initial conditions are 0. Write an expression for the Laplace transformation, right, of the differential equation in part E above. So that's this here, right? So we just put that, right. So we put that again, right? X at t minus a1 dy dt minus a2y at t equals d2y dt squared, right? Now, first, if we do these, if we make these substitutions, you're going to get x1 at t is minus 7 dy dt minus 12y at t equals d2y dt squared. And if we were to convert that into the Laplace, or transform that into the Laplace domain, x of t gives you x of s, right? dy dt is equal to s y s, so that's 7 s y s. Y at t is equal to ys minus 12ys, and then d2y dt squared is s squared ys. Now remember, we looked at the properties briefly. This is one of the big things about the properties here. So when you differentiate in the time domain and you convert that to the Laplace domain, it's just s in front of the x of s. And if it's a second order differential, is s squared, third order differential is s cubed, etc. So that's why in doing these calculations in the Laplace domain is much easier in terms of computation, right? All right, so that's your y, that's your that's getting your right, that's putting the expression or transforming the expression into the Laplace domain. Right, now you could use this to get your h of s, just like in the previous example. Now we're going to get h of s, and h of s is y of s over x of s, right? So this is what we had here when we transformed it into the Laplace domain. X of s minus 7s y of s minus 12y of s equals s squared y of s. And if we just bring across all the y values, and then we put all the y values on one side and all the x values on the other side, s squared y of s, so this remains here. We bring across the 7, it becomes plus 7 s y of s, bring across 12, plus 12 y of s equals x of s. And the function h of s is y over x, right? So similar to what we did last time, right? So we're going to divide both sides by x of s first, and then divide both sides by s squared plus 7s plus 12. Right. So now we have the h of s is equal to 1 over s squared plus 7s plus 12. And we can break that down even further. If we factorize this, you're going to get s plus 3, right? Multiplied by s plus 4. Right? So if we multiply that, you're going to get s squared plus 3s plus 4s plus 12. 3 and 4 is 7. So s squared plus 7s plus 12. So that's why I break down this here. Right. Okay. So now that we have h of s, right, and they're giving us what x of t should be, right? X of t is e to the power of 4t u of t. They want you to find out y of t. So this is where we're going to go through the whole thing where we first convert the x of t into x of s. Now, the reason why we're going into x of s is because this is a continuous time signal, right? So we can't do Z transform, we do Laplace transform. So we transfer x of t into x of s, and then we multiply x of s by h of s to get y of s. And finally, we're going to do the inverse Laplace to get it back in the y of t. So in this case, we have to use partial fractions because it's not going to work out, but we'll see how it looks. Okay, so first we have x of t, and that is e to the power of 4t u of t. So now we need to look at the tables, but this time we're looking at the Laplace tables, right? And same thing. So we're looking for something in the time column, right? So we're looking for the time column. We're looking for something in the format like this. And if you scroll on, well, I've highlighted here already, e of minus at u of t, right? Where a is 4. And if you do the Laplace transform on that, you're going to get 1 over s plus a. A is 4, right? So the Laplace transform of e minus u minus 4t u of t is equal to 1 over s plus 4. Right. I just want to you're all okay with this table, right? You saw that how we was able to transform using the table, okay?
Yes,
Yeah.
sir.
Okay, good. As I say, listen, I know the topic is new, and as I mentioned earlier in class, right? It has a lot of maths in it. But don't worry, we'll do some more examples, right? We'll do some more examples next class also to get you familiar with it, right? So just see how much you could pick up now, and then you could review over the next week. Yeah, Kelda.
Yeah, I just feel exhausted. That's a
I
lot
know.
to take in, as a lot.
Yeah, I agree. It is a lot. Is real heavy on the math. This is a lot of maths. Just to tell you, this class is going to have this topic is going to have a lot of math, and then we're going to do Fourier transforms, which is also a lot of math, right? But just hang in there. Just try to follow as much as you could. Look at the
Yes, because I follow along with what you're saying, but if I try to write down while I talk, I pressure.
yeah.
So
I can.
I'll review the recording and take my time and write down.
Yeah.
So,
Yeah,
but
when I try to, I getting confused. I don't know. I don't know what.
No, don't worry about it. It will be like that. But I will do enough examples. So this week, make some time and just review the slides or the lecture recording and the slides if you need to just sort of follow what I did. And next week we will do some more examples. So that'll be like like looking at something else, and we will go through it again, and I'll get you all comfortable enough with it. So don't worry about it. Just try to see as much as you could follow.
yeah, it's just a matter of familiarity and that should be it.
Yeah, it is because there's a lot of concepts. Is the Laplace and Z, then is the partial fractions. So I'll look at
So I see you have e to the power -4, right? Will it always be a negative number?
no, it could be a positive, but if it's a positive, then it will switch the sign here.
Okay.
So this could be s minus a. Yeah.
All
right. But we do some examples, so you'll see some different variations. I can't promise you'll see all the different examples, but some of the main ones that we will cover in class.
So
Okay.
for example and stuff, you'll give us a partial thing, that long thing to do. That partial
For
Um,
exams, don't worry, for the exams, I will make sure you're all prepared with it. Right. And
well,
yeah, so don't worry too much about the exams. Whatever you all get, I'll make sure you have enough practice with it that you'll be familiar. Right. So for now, yeah, so we'll go through that. Okay. Right. So the first thing is the transformation of the x of t, right, to x of s. Second thing is you want to get your whatever you have your x of s that we just did, and you have your h of s, right, which we got 2 slides ago, right, which is this one. So now you're going to find your y(s), which is your x of s, the 1 over the s plus 4, multiplied by the h of s, which is 1 over s plus 3, s plus 4. And that will give you 1 over s plus 3, s plus 4 squared. Now, if we look now in the table, because we have to convert it back to the time domain, right? In the table, we have a value in s plus a, and then we have a value in s plus a squared. I shouldn't say value, but we have a format in this format here, s plus a and s plus a squared, which kind of matching what we have. So what we need to do is we need to break this 1 over s plus 3, s plus 4 squared further down using partial fractions, because right now this is the denominator. It is just one denominator, right? So we need to have it as 2 separate fractions. Now, how we separate this, we look in the partial fractions table here, this main table here. And for the first part, the ax plus b, right, which is the s plus 3, right, denominator, we could decompose that into a over ax plus b. But the second part, which is the s plus 4 squared, it looks more like this. Ax plus b to the k. Now, you might be saying that, okay, s plus 4 squared, you could use this format here also, right? But this would be a easier format for you to use. Okay, so essentially what you're going to do is you're going to say 1 over s plus 3 multiplied by s plus 4 squared is equal to a over s plus 3 plus b over s plus 4 plus c over s plus 4 squared. And that's because the 1 over s plus 3 giving you straight this here, right? So using this for the s plus 3. For the s plus 4 squared, you're going to get a1 over s plus 4 plus a2 over s plus 4 squared, right? So you have to go into 2 different parts there for that. Right. Now, same like before, you multiply, you try to get the common denominator, right? So you multiply, right. So you would multiply by s plus 3, s plus 4 squared, everything. And you're going to get, for A, you're going to be s plus 4 squared because the s plus 3 already there. For B, you're going to get s plus 3, s plus 4. And for C, you're going to s plus 3, right? Because s plus 4 squared here. And the 1 will be there only because s plus 3, s plus 4 squared is already denominator. And then next, you go and to substitute some values for s to eliminate the other values, right? So if you substitute s equals -3, you're going to eliminate B and C, right? So you're going to get -3 plus 4 is 1. So it's a1 squared plus, well, B goes to 0, C goes to 0, right? So 1 squared is 1, so A is equal to 1. And if you substitute s equals -4, you're going to eliminate A and B, right? So eliminate A, eliminate B. C is going to be -4 plus 3 is -1. So minus C equal 1, C is equal to -1, that's C. And to get B, you could substitute a value for A and C, you already have that. And for S, you could just substitute the easy value like 0. Okay, so when you work that out, A is equal to 1, S is 0, so you can get 4 squared, right? B, we're trying to find B, so S is 0, so it's going to be 3 by 4. And then C is equal to -1, right? S is equal to 0 multiplied by 3. So you're going to get 16 plus 12 minus 3, right? So you're going to get 12B is equal to 1 plus 3 minus 16, that's -12, and B is equal to -1, right? Right. So now, in terms of partial, when we use the partial fractions, we broke up the 1 over s plus 3, s plus 4 squared into, well, this is the general thing, right? A over s plus 3 plus B over s plus 4 plus C over s plus 4 squared. So now that we have that, we need to now convert or do the inverse transform to get it back in time domain. So let's look at the first value, 1 over s plus 3. Again, now we're looking at time. Now remember, we need S domain going over to time, right? So you're looking at this column. So this looks like a format here, S plus A. So 1 over S plus 3 is equal to E minus 3t U of t, right? So that's the first one. Second one, 1 over S plus 4, well, the same format we could use. You're going to get E minus 4t U of t. And the final one, right, we actually have something here with S plus A all squared. And that's going to give you T E of minus AT U of t. So that's T of E of minus 4, because A is 4, T U of t. So finally, right, U of t, minus U of t, Y of t is equal to E of minus 3t U t, right? That's the 1 over S plus 3, minus E of minus 4t U of t, that's the minus 1 over S plus 4, minus T E of minus 4t U of t, right? Which is the last term here. And if we factorize out the U of t, we just put in the brackets now, E of minus 3t minus E of minus 4t minus T E of minus 4t. And that will be the answer. Right? So, yeah, so that is, that's how you solve for the equation there. Okay, so if you notice, these steps are generally the same, which is you finding the system equation, right? Y of t in terms of x of t. Then you finding the Laplace transform. So y of s is equal to h of s x of s, right? And then after that, you would get your h of s. Then they will give you an input. You convert that or transform that into the Laplace domain. And then when you convert the input in the Laplace domain, you multiply by the h of s, right? And that will give you the y of s. And now that you have y of s in Laplace domain, you need to convert that back or transform it back into the time domain. And for that, you use the tables. Okay, so yeah, so it's quite, quite a bit of maths, right? The process is the same, right, for both the Z transform and the Laplace transform, right? So the process is the same, where you find a system function, you find any h of Z or h of S, you convert in your input into the other domain, you do the calculation, and then you're doing the inverse. The only thing about the inverse is, depending on the format of it, you will need to probably do partial fractions to get it to break it down even further. All right. Okay, so yeah, so I think what would be good, what you should do is this week, because there was a lot of new stuff, right? Just if you could go through the notes and go through the lecture and see if you could follow the example, right? If you could follow the example, and then next week we will do some more questions, right? So to give you some more practice with it, it should be okay.
Recording stopped.
Right. Any questions? Well, other than that, because I know some of you might have a lot of questions about this in particular, right? But anything you want to clarify?
Yeah, I just want to, I finished the assignment, but I want to just look it over. Yeah, I just want to recap what you said. You said I could upload the assignment after midnight, right?
Yeah, I put the okay, so the on Canvas there are two sort of timelines you could put, right? There's a deadline for the assignment, and there's a well, that we call it available. So basically, how long the assignment will be up for you to upload information. So the deadline for the assignment is tonight, right? But I'm leaving the link open until next week. So when you upload, if you upload after tonight, midnight, it's going to be uploaded and it's going to just be like categorized as late, but it still is going to be, I will still have access to it. You all will not be penalized for late submissions, right? So if you want some extra time,
Okay.
you could.
Okay,
I just please try to upload it before next week, because if the link closes, then it'll get messy to get it back. Anybody else have any questions about the assignment? When in terms of submission or anything like that?
Oh yeah, excuse me, sir. For the, you know how, well, the first part asks you to write out, well, get the equation for the all the different signals, but like for
signals,
the
yeah.
other questions after that, what do you have to rewrite the same equation you've found for part A over, but just add in the new different operations, or you just have to sketch the graphs? So,
No, just sketch the graphs.
all right.
Let me just pull it up to make sure we're on the same page, right? Hold on. Let's get it. Okay, right. So this is the assignment. Okay, so for the first question, first part, so part A, it's exactly as you said, right? So you need to determine what is the equation or the different signals that make up x of t. So this one is only unit step functions, right? So it's going to be a equation with only unit step functions. For part B to F, you don't need to rewrite the equation. All you need to do is just sketch it, right? Just sketch the transformation or the transformation as applied to that signal. Clearly show, where it crosses the axes, etc. And also very important, describe the transformation, right? So if it is a time, if it's an expansion, compression, time reversal, time shift, amplitude scaling, put that in it. Don't forget to put that in your answer. And same thing for the second one.
All right.
Okay. All right. Okay. Any more questions on the assignment or anything?
Not well for me, none right now. So probably by next week, you have something about like what happened in class with all the maths.
Yeah. So yeah, with the lecture today, yeah, it is a lot of math, as I say. Review the lecture, right? Review the slides, and if you need to review the recording, and see if you could, at least follow the example, like the different steps, right? See if you could follow the examples. Next week we do some more examples, right? We do some more examples, and you'll get a better understanding, right? Also next week, well, yeah, okay, yeah, right, yeah, I think that's it, yeah. So next week we'll do some more examples on the Z transform and the Laplace transform, and I think together with reviewing the lecture today and next week, I think everyone should be okay, but we'll go through it to make sure everyone's okay.
Find this course have a lot of stuff to cover.
Yeah, the maths is a
Yeah.
bit heavy in this course compared to a lot of the other courses. This because signals and systems is a topic that yes, these systems are using telecommunication systems, but it's used a lot in electrical and control systems. So in electrical engineering, this topic is a major topic. A lot of maths is done for that.
So, sir, if I go into the telecommunication field, I have to do a lot of maths?
Well, it depends on which side you go in. So this one, it has to do with like the signals. So like if you look at the amplitudes coming in, the signals coming in from the radio waves, and then you're breaking it down, then you'll have to look at it. But the other thing too, the way how the working industry is, they have different fields, right? So unless you really working on the field that works on the RF and this sort of thing, you may not have to, But the thing about it is these courses, like when you do your degree, your computer engineering degree, etc., they put together courses to touch on fundamental areas for the broader field in general. So that's why you touch on like signal systems, you do a little bit of networking, you do a little bit of database management, you do software engineering, this sort of thing. So you come out like sort of well-rounded in different different disciplines within the overall degree, which is a good thing.
So wait, it's trying to like give you a little bit of everything you would possibly see in the industry, but at a fundamental level.
Yeah, well, the major stuff at least, yes, the major stuff.
All right.
So which one is pretty good because of all our work we do, we gotta get a good salary. Let's try to-
Well, the pay is a combination of things, sir. The pay is the work you're doing and then the company you're working for. That's them. Sometimes the company you're working for is the bigger part of it.
So which is in your opinion, which is the best company to work for in telecom?
These the international companies is the better company to work for. But it's to get to get hired by them. Sometimes they just have like they have open vacancies. Sometimes, many times is somebody you could connect with who could kind of refer you to it. Many times it's like that.
All of that seen is entry level with 5 years of experience. That's all I see.
Yes, but that
No,
is a rough thing out there in terms of vacancies and things like that. But you gotta keep trying. What you do is like in situations like that, you just gotta keep building yourself. I mean, opportunity will come. It will come. You just gotta make sure that you keep moving, so that when the opportunity does come, you are at your background well developed, and you can get the opportunity. So these things just helps with it, because some of the principles and these things is carry over, because sometimes when they hire for a job, the job description, sometimes it's not complete and you just focus on one thing, like one specific thing. You might be focused only on doing something with like routing or network with routers only, or you might be working on a certain part of software or databases, etc. But we don't know, unless you have something lined up already. You don't know, you're not sure exactly what position you're going to be in. And that's why the degree is a good thing, because it gives you that broad knowledge of many areas. And then when it is you finally get your job and you get an area, you could adapt it quicker. So I think, like, for example, the embedded systems course, I think is a really nice course because that hands-on experience on the devices is really good. Really good. Because essentially when you go out to work, that's what you have to do. They're going to have specific equipment that you have to work on. You have to learn how it works, and you need to make different configurations and make it do things that specific to the company needs. Right. Oh yeah, so embedded systems will be in class tomorrow, right? And campus. Yeah. Work with your flash drives also.
Oh yeah, excuse me, sir. This is regarding embed systems. It's if we bring our HDMI to HDMI or pure HDMI, would that be all right?
Yeah, I think so. Given how things went the last 2 classes,
Yeah,
if you have
because
your
I don't know how if since you said by next week you'll be get everything sorted out, but I don't actually. I just want to come prepared if something unfortunate happens.
yeah, so that's what he said last week. So I don't know. But if you have the HDMI cables or the adapters, yeah, you want to bring it for sure. I think someone said they were going to bring a monitor and things like that. So I don't know.
I think that was Kieran, but whom? Is that him or somebody else?
But yeah, let's hope at least they have at least what was working last week. I think groups were pretty okay last week, and we work with that, right? So I'll let you know more about that tomorrow. So meet you all tomorrow at 5 p.m. Embedded Systems people. The signals persons. If you have, well, generally the class has no more questions. As I say, review the lectures, see as much as you could follow. Looking at the notes and the recording if you need to. And next week we'll go through some more examples to kind of firm up on the understanding of it. I think everybody will be okay next week when we go through the class, just with the additional examples. So Right, so if no more questions, everyone, thank you again. Thank you for your patience tonight. You know, there's a lot. And I'll see the class next week, Signals and Systems. Right. So take care, have a
Alright.
good night.
Right.
That's